Hi, welcome to the Calculus 2 lecture series. And this is unit number 1. We are talking about different kind of the applications of integration. This is our lecture number 4. And we are going to take a look at physics application is the work, how to find the amount of the work done by varying the force to moving an object. First, I want to kind of make sure we are not teaching the physics here. We just take a look at one of the physics applications. How do we use the integration calculus to help us? And I also think for most of the people, if they are taking the calculus 2, they probably already have some very basic fundamental of the physics concept. So the way I like to approach this lecture, we're just going to have some very basic definition about the several physics terms and then see how the integration can apply. All right. Okay, so now let's go ahead, go to our worksheets here, the lecture notes here, all right? So let's take a look. So the key concept for the, for this lecture number 4 is we're going to talk about this work, like we talk about is how to calculate the, so we want to calculate the work done by a varying amount of the force. Okay, along an axis. Okay, so also, this axis could be a line, so or could be like, the curve. So that's why we say just in general, it's an axis here. How much what is type of the total? How much work has been done by varying amount of the force? All right, along a axis here. Okay, so we know so let's take a look at what is the definition of the work here. Like I said, the way I would like to approach this lecture, basically, we just go kind of review some basic physics definition. So what is the work? Work is the measure. Work is the measure of the effort expended by moving an object from one point to another. Okay, so when you talk about the reason why we can kind of use the calculus concept to calculate the work. Think about the total work done, like from moving. So if you think about the total work done from moving, for example, from moving the object from here to here, right? So you really can think about it as kind of like the work done. You can put it into several very small sub-intervals here, right? So you can put a small sub-intervals here. So the total amount of work done would just be, you add those work done move from here to here, here to here, here to here, right? So you add all those sub-intervals together. That will be the total work has been done moving from this point to here. So we know when you do this summation of the sub-interval, that's why we can that's why we know the total amount of the work we can determine it by a definite integral. See here, that's the reason why see here. All right, so that is the the work definition is the total measured effort. So moving the object from one point to another. The reason why we can use the can be so we can be determined by a definite integral That's why we say it's one of the application is because you can think about these paths here, right? So we can divide it into many sub-intervals. Then we can add each sub-intervals, the work together to get a total. Now if you can divide this sub-interval to the infinity number of intervals, that's what we call it is the integrations here, all right? Okay, so the first things here, like I said, we're going to have some very basic definitions here. So the first is the mass, all right? So the mass, the unit, not a unit, the notation we use is the ants, right? The mass, so we say the mass of an object measures the amount of the matter. Amount of the matter in the object. Okay, so the first things here, we're going to write here. So what is the SI units for the mass? I use a different color. Okay, so the SI unit for the mass, so the unit we typically use for the mass is the kilogram. Okay, then the next things here, we say how the mass can be calculated. Okay, so we know the mass can be calculated as the density, of the object times the volumes here. Okay, so this is how do we calculate the mass? Is the density times the volume. Okay, so now the next definition is what we call is the force here. Okay, so what is the force? The force here can be, the force we can say you can push something or you can pull something, right? So both is the force. So the force on the object is the, so is the object's mass times the acceleration of its motion. Okay, so now let's take a look what is the SI unit here. So for the force, the SI unit, okay, so we typical is to use the newtons, right? So we say it's the Newton. So the way we define the newtons here, so it's 1 Newton will be 1 kilogram, right, times m seconds square, right? Because it's accelerations, right? So like for the typical, the Earth's gravity is acceleration. So it will be 9.8 meter per second, right? So this is the unit for the acceleration is the meter per second. So if you are trying to find, in the Earth, the gravitation here is 9.8 here, right? So that's what we call is the force. Then what is the weight? Okay, so a weight, right? So it's a special force. Okay, and the weight is due to the Earth's gravity. Okay, so the weight will be, the way we defined, right? So let's say the weight is calculated is the mass times what? Times the gravities right here, right? So it's a G. G is 9.8 meters per second here. So depends on, like if the, if you want to find the weight in the moon, then the gravitation here will be different, right? So here for the Earth here, the gravity is what? The gravity will be the 9.8 meter per second squares, right? All right, so now, okay, so we're going to talk about another one. So then we can start to take a look at some very basic example. So it's a constant force. Okay, so what is the constant force here? So the constant force is the work, okay, done. So we know the done to move. So force is the object, right? So it's you push or pull an object, right? So it's the force to move an object a distance d with a constant force. And this constant force, I called it, is F. So in here, our calculations here, so the force will be equal to what? Force will be equal to this, the work will be equal to the force times the distance here, right? Okay, so now let's take a look also what is the SI unit for the work. Okay, so the SI unit for the work will be, we call this the force times the distance, right? So will be kilogram, and now the distance is m, and times the, the gravity, the acceleration, so it's m square to the what is the second square. And this unit here we call we call this joules, right? So this is J, that's what we call it, the joule here. All right. So like I said, those are some very, very fundamental definition about the physics. What is the, what is the mass, force, weight, and the work? How do we define it's moving the object from one point to another? Then finally, we said we're going to define the force. So the first one is here is a constant force. So it's a constant force, and then the work is pretty easy. Will just be that force times what? Times the distance you move here. All right. Then the next thing we're going to talk about, how about your force is not a constant. Now, what do we do here? Okay, so let's take a look at the first ones here. The first one, this example is very easy. Let's say if a 2 kilogram mass block is lifting 3 meters off the tables here, then what the work done by doing so? Right? So I know, okay, so it's lifted by, okay, so this is work is equal to force times the distance here, right? So let's back to here. What is the force? The force is the mass times the acceleration, right? So force is newtons. So force is the mass times the acceleration. So it will be the 2 kilogram times, because we are on the Earth. So what is the acceleration? Is 9.8 meter per second square. Then what is the distance? Times the 3 meter. Okay, so now as you see, all this unit matches, so you know you're going to get it correct. So this will be 19.6 Newton times 3 meters, right? So this will be what? 58.8. So if you put all this unit together, it will be kilogram meter square, the second square. So what is this? This is joules, right? So it's a J. So we know we're going to, so what is the work done? So the work done is 58.8 joules here. Right. Okay, so now let's take a look at the second one here. The second one is that how much work is done by lifting a piano weight 800 kilogram up to the 6 meters here. Okay, so the force for this problem is the 800 kilogram is because this is already is the weight, right? So now we say the work will be the force. So the force in here is already, so it's 800, then just do what? Times what? Times 6. So it will be 4,800 joules. Yeah, right? So in here, those are the very, very basic and very simple problems here. Okay, so varying force is here. Okay, so what is varying force? That means, you know, if an object here, so let's take a look at how about the force is not a constant force anymore. So that means if an object here can move along x-axis, let's just say the easy x-axis from A to B by varying a force f of x. Okay, so then what is the work done? So just like we talked before, right? So I'm moving, you know, object from here to here, right? And but my force here is not a constant. So sometimes maybe I push more in this interval, now I'm getting tired. I push less, then I push like even less, then I after a good rest, I push more. So my force is not a constant force here. So what can you do? So like we say, just like we did in the Riemann-Sum concept, you can calculate the force, you can calculate the work by each sub-intervals here, right? Then you add them together. So that is what happens, the integration come to play. So for here, you know, like this one, basically, you can say the total work will be done, will be the f of xi and the delta xi, right? So from I from 1 to n. So you divide it into several sub-intervals. And then for each interval, they have a distance to travel, they have the different the force to push or pull it, right? So the total work for the, you know, the varying force, so the total work here, if your force is not a constant, so the W will be equal to what? Will just be equal to, like we simple the f of, you know, you integrate from A to B, then is what is f of x dx will just be, you integrate, you know, for each sub-interval, you have a different force here. Okay, now let's take a look at the example number 3 here. So example number 3 is that how much work is done moving a particle along the x-axis from 0 to pi to over 2 feet. If at each point x, the amount of the force is a cosine x pounds here. So that means in here, my force is depend on the where is the axis here, right? So based on my simple varying force formula for the total work, so I know my work is what? It's just integrate my force function. So will be the cosine x dx. What is the distance I travel from the 0 to where? To pi over 2 here, right? So I know this one is simple, so it's sine x from 0 pi over 2. So this will be 1, but here be careful, right? So this is pounds, right? So pounds versus foot here. So it's 1 ft and the pounds. So that would be the unit if you use the pounds here. Okay, now let's take a look at problem number 4 here. The problem number 4 is kind of like a very good problem. It's kind of put all these things together and see how we do that. So in here, they say find the integral for how much work is done in pumping over the edge all the liquid of the density, rho, all right? So I give the density of the liquid. I don't know what type of the liquid is the rho out of the 2-foot long trough in the shape of equilateral triangles here, okay, with the side of 1. Okay, so in here, so what is the first? I want to find the work, right? So basically, just like the varying forces here, you divide it into the subintervals here, right? So basically, so the work done, so the way we look here, the work done to pump a thin slice. Remember the Raymond-Sun concept, right? Thin slice of the liquid. Yes, all right, so here. So we know, okay, so what is the work done here? So density times gravitational G and times the volume, right, times the height. Okay, so let's see what are all these things here, right? The height, okay, so first let's take a look at height. That is really is what? That's the distance, right? That's the distance. So you want to pump out here. So the volume, so density and the volumes here. So here, if you take a look, we say the density, right? So here, the mass is density times the volume. All right, density times the volume, and then you times the, the gravitation constants. That is your what? That's your force here, right? So basically, okay, so this whole thing here. So this whole thing here is what? This is the force, correct? So this is the force. All right, so this one's here, let's put a little bit better. So the density and the volume, these two is what? These two become a mass. So mass times G is give you what? Mass times G give you what? Give you the force. That's right. So that is what the mass times. So here, right? So the force is the mass times the accelerations, right? So it will become your force. So then these things here will just be the force times the distance. Then you slice it just like in the interval, you divide it into several sub-intervals. So in here is the same way, you slice it. Simply imagine that you can have a thin slice of the water you pump out. All right. So let me do a picture. So maybe let's try to solve these problems here, right? So let's see here. So let me say, imagine here. Oh, I hope I can do good. So imagine this is the thin slice. Okay, so this is the thin slice of the water. Okay, I hope I can do this. Oh, maybe I did it. Okay, so imagine that, right? So this is the thin slice. Okay, so this is the slice of the water you want to pump out, right? So just like we divide, like when we are moving the things, right? So you divide it into a subinterval. So this is, you just slice it, right? Okay, so now, and now we are get a good start here, right? So let's take a look at how do we do that. So now the first things here, let me do this. Let me put x-axis here. So maybe you will be easier to see. So let's take a look. If I say this is my x-axis here. Okay, so now those things I need, right? So I need my, so I know here, all right? Okay, so now in first things here, let's take a look, see here, the height raised, okay? So, okay, so first things here, the side is the equilateral triangles here, all right? So the side is equilateral triangle. So that means let's put, this is my side. So it's an equilateral triangle. So this is 1, this is 1, this is 1. Am I right? Okay. So if you're here, you have then this side is 1/2. This side is 1/2 because it's equilateral. Okay. So if equilateral triangle, then what is the height here? Right? So the height here, this is a special triangle. So what is the height here? The height will be the square root of the 3/2. And right, so this will be the square root of the 3/2 here. So that means I know they intersect here. So this is the square root of the 3/2. That's the total height of this trough here. Okay, so now this is like the thin slice we cut, right? So this is very thin slice. So this is my delta x here. All right, and then this one's here. Let's see here for this side here. Let's say here, right? We say this is the x value, right? So this is my x stars here. Okay, so let's see here. So then what is the how much? So like in here, okay, so if you take a look here, if from here to here, the distance is xi star. All right, so this is the xi star. That's what this is the slice of the water I try to pump out. Now, how high I need to pump that out? High. The total is the square root of the 3/2, right? So how high I need to pump that out is the square root of the 3/2 minus what? Minus xi squared. Correct? Okay, so this is my D, right? So this is my D, is the square root of the 3/2 minus xi squared. Okay, now I need to find, I already know the density. Density is rho, the constant is 9.8. Now I need to find this volumes here. All right, so now the things here, I need to kind of find this volumes here, right? This is thin slice of what? Rectangular prism volumes here. All right, so let's see, how do I find it? Okay, so in order to find the volumes here, so if, okay, so if I put this slice out, so this is basically is my thin slice of waters, right? So I know that this side, this trough, this length, this is fixed, right? So this is the 2. And this height is fixed. This is delta x. So now I need to know this side, right? I need to know the width here. So I need to know this side. That means this blue side, right? So how much, what is the value for this blue side here? Okay, so let's take a look again, right? All right, so let's put this triangle, the house in here again. Okay, so this is the equilateral triangles here, right? All right, so I know this side is 1. All right, and we already calculated from here to here, the height is the square root of the 3/2. So this side really is here, huh? Right, so it's in here. Right, so if you do a cross section, you see here, so that's the really is here, right? So I want to know what is the, what is this length, right? And I know in here, I already know this is xi here. This is xi stars here. Okay, so now let's see how do we do it. So I assume this one is the X, right? So by the similar triangle, right? So by the similar triangle, okay, the big ones here on the similar triangle I'm talking about is these big ones here. Okay, versus this small one here, all right? Versus this small triangle here, all right? This small triangle. Okay, so now the 1 divided by x, so 1 is this big one, the small one is x, will be equal to, the height is here, right? The height for the big one is what? It's the square root of the 3/2. So what is the height of the small one? Is xi, right? Xi star. So what is x here? So x will be equal to what? X equal to the 2 of the square root of the 3, the xi. So I know in here, so this will be the 2 of the square root of the 3, the xi. Right? So now I have so I know the volumes here, right? So what is the volumes here? Okay, so the volumes here, let's try to here. So the volumes here will be 2 times the length times width times the height. So it's 4 over square root of the 3 xi star times delta x. Correct? Okay, so now I finally can substitute to these formulas here. This is the thin slice, right? So if I want to find the whole water, I'm just integrating. So from 0 to the top, what is the top? The square root of the 3/2. Okay, so density, so is rho, right? So density, okay, so density times the acceleration, the volumes, we just calculate what is the volume here, is the 4 over square root of the 3x, right? Then what is the height? The height will be the square root of the 3/2 minus x, right? Then the delta x will become our dx. So that will be the total amount, right? So this will be the total amount of the work being done when I pumping the water out of these troughs here. All right. Okay, so since they did not give us the density function, so if you calculate this integration, so I guess the final answer for this integration, okay, so final answer for this integration, the work, if you calculate that, then we know the integration, so the total. So let's rewrite it, square root of the 3/2, right? So it's the density times the acceleration factor times the x times square root of the 3/2. I'm sorry, here, this is the 4, the volumes here is 4x. So it's 4x, the square root of the 3, and then this is the square root of the 3/2 minus the x dx. So with density and the gravitation unknown, but you can treat them as constants. So the final answer will be rho g over 4. Okay, so that's the amount of the work if you want to pump out the water from this trough here, right? So it's a very similar idea like we talk about when we do the the bearing force, right? So just like instead of divided into each sub-interval, then you integrate that, Now here is like we kind of the similar, we have each slice, we pump out each slice. So each slice when pump out, the force will be, we talk about the force, right? So the force in here will be the density of the liquid times the gravitation times the volume and times the height. You need to try, pump it out, right? So that's how do we try to find all the values based on that. All right, so that's it. And of course, this is just a very, very basic physics applications. And I want to let you know, the integration can be used in the physics area. And that's just a simple application to show you, how to apply it. All right, that's it. And hope for the physics majors, you'll find that this is pretty easy, right? All right, that's it. Have a nice day, and we're going to talk about our last applications in our next video. Okay, talk to you later. Bye.